The development of space-based navigation systems commenced in the 1950s with the establishment of the United States Department of Defense Transit System. The current generation began development in the 1970s, and the next generation is already under development. It is intended that Global Navigation Satellite Systems, or GNSS, will eventually replace all terrestrial radio navigational facilities. However, despite USA assertions that this is imminent, it is unlikely to be achieved in the foreseeable future. The current systems have brought a new dimension of accuracy to navigation systems, with precision measured in meters. And where special differential techniques are used, the potential is for accuracies substantially less than 1 meter. Navigation packages for aviation based on the United States Department of Defense Global Positioning System, or GPS, are now widely in use. However, 4 other satellite positioning systems are either in service or are planned to enter service in the next decade. The Russian GLONASS and European Galileo systems are well known, but it has recently been announced that China and India both intend to launch independent systems. The Chinese one is called Beidou, which means compass in English, and the Indian one is called INSAT. The EASA ATPL syllabus requires you to know about 3 systems: the Navstar Global Positioning System, GPS, operated by the USA, the Russian GLONASS system, and the European Galileo system. In order to understand the operation of these GNSS systems, we need to look at Kepler's 3 laws on planetary orbits. The first of these states that a satellite's orbit describes an ellipse with the Earth as one of the foci. Let's start by explaining what an ellipse is and what these foci are. We'll begin with a circle. We define a circle by starting with the center, then producing a radius of a constant length, and then we rotate the radius through a revolution. With an ellipse, we have 2 starting points, not 1. These are called foci, which we'll label F1 and F2. If the distance from F1 to the edge and back to F2 always stays the same, then by definition, we have an ellipse. To make it an Earth orbit, we'll put the Earth at F1. F2 can now be ignored. The second law states that a satellite sweeps out equal areas in equal time. The orbital velocity is constantly changing with the distance from the Earth. It is fastest when nearest the Earth, and then slows down, reaching a minimum at the furthest point. Kepler was the first person to find the relationship which describes how the speed changes. Kepler's second law is that the line joining the satellite to the Earth, known as the radius vector, sweeps out equal areas in equal time. This is the radius vector. This is how far the satellite moves in a fixed time, such as an hour, when near the Earth. However, when it is at its furthest point, it is travelling slower. In the same time interval, the distance travelled round the orbit will be less. Kepler's second law states that if the grey shadings have the same area, the time will be the same. There is a third law which states that the square of the satellite's orbital period is proportional to the cube of its average distance. But we do not need to go into detail about this law. Global navigation satellite systems use an Earth-referenced three-dimensional Cartesian coordinate system to define positions, with the origin of the coordinates being the center of the Earth. Because the GNSS systems are global, a common model of the Earth was required. The World Geodetic Survey of 1984, WGS 84, was selected as the appropriate model for GPS. Galileo uses the European Terrestrial Reference System, ETRS 89, and the Russian model uses Parameters of the Earth, PZ 90. The mathematically produced models of the Earth are regular shapes, called ellipsoids. But these cannot be a perfect representation of the Earth, a geoid shape, nor can they represent geographical features such as mountains and oceans. The distance of mean sea level from the center of the Earth depends on gravitational forces, which vary both locally and globally. So, mean sea level will not necessarily coincide with the surface of the ellipsoid. Hence, the vertical information provided by any system reference to this model cannot be used in isolation for vertical positioning, except when in medium or high-level cruise with all aircraft using the GNSS reference data. GPS comprises three segments: the space segment, the control segment, and the user segment. The GPS space segment nominally comprises 24 space vehicles, SVs, that is, 4 satellites in each of 6 orbital planes. 21 of these are operational and 3 are spares, to be activated in the event of a breakdown. But because the satellites have exceeded their design lives by years, there are actually 31 working satellites in orbit at the time of production of this lesson, which is September 2011. The orbits have an average height of 20,180 kilometers, an orbital period of 12 hours, an orbital plane inclination of 55 degrees, and they are equally spaced around the equator. The spacing in their orbits is such that an observer on or close to the surface of the Earth will have between 5 and 8 SVs in view at least 5 degrees above the horizon. An SV will be masked, that is, not selected for navigation use if its elevation is less than 5 degrees above the horizon. The space vehicles, SVs, broadcast pseudo-random noise codes, that is, a message that is so long that it appears to be random, but it is in fact repeated at a given interval. The code lasts for 1 millisecond, an epoch, and it is unique to each satellite. And it is transmitted on 2 frequencies. The L1 frequency transmits a carrier wave on 1575.42 MHz. The information it broadcasts consists of a course acquisition, or CA code, repeated every millisecond, with a modulation of 1.023 MHz. The precision, P code, repeated every 7 days, with a modulation of 10.23 MHz, and the navigation and system data message with a modulation of 50 Hz. The L2 frequency transmits a carrier wave on 1227.6 MHz. It broadcasts the P code and is used to determine ionospheric delays. Only the course acquisition code and the nav and system data are available to civilian users, whereas the CA and P codes, as well as the nav and system data information, are available to the US military and other approved users. To protect the GPS from fake satellite transmissions, anti-spoofing measures are adopted. When this happens, the P code is designated the Y code, and it is encrypted, so that it is only available to those with the necessary decryption algorithms. So, there are two levels of service: the standard positioning service using just the course acquisition code, and the precise positioning service using the course acquisition and precision codes. The information contained in the navigation and system data message is used by both services. It consists of the satellite vehicle's position, its clock time, and clock error. It also contains information on ionospheric conditions, which affects the accuracy of the signal, and supplementary information, including the almanac, that is, the orbital parameters for the SVs, the SV's health, and other time, command, and control functions. The GPS control segment comprises a master control station, a backup control station, and monitoring stations with antennae. OCS stands for Operation Control Segment, and NGA stands for National Geospatial Intelligence Agency, who provide precise information to correct orbital data. The monitoring stations check the SV's internally computed position and clock time at least once every 12 hours. Although the calculation of position using Keplerian laws is precise, the SV orbits are affected by the gravitational influences of the Sun, Moon, and planets, and solar radiation. So errors between the computed position and the actual position occur. When a positional error is detected by the ground station, it is sent to the SV for the SV to update its knowledge of position. Similarly, if an error is detected in the SV clock time, this is notified to the SV, but since the clocks cannot be adjusted, the error is included in the SV broadcast. We said earlier that the ATPL syllabus required you to know details of GPS, GLONASS, and Galileo. These systems all operate in very similar ways, but there are differences which you are required to learn. Here is a table showing the differences. Number of satellites: 24 for GPS, although 31 are in place at present, 24 for GLONASS, and up to 30 for Galileo. Number of orbits: 6, 3, and 3. The inclination of the orbits to the equator: 55 degrees, 65 degrees, and 56 degrees. Satellite altitude: 20,200 kilometers, 18,840 to 19,940 kilometers. and 23,222 kilometers. The duration of one orbit, 12 hours, 11 and a quarter hours, and 14 hours. These are the transmitted signals. The L1 signals have the following codes: CA, which stands for course acquisition, and P, which stands for precision. Civilians and the military are able to access the CA signals. The L2 signals have only P codes, and these are available only to the military. Timing is achieved using atomic clocks, and different systems have different ellipsoids, but they can be converted so that they are compatible with each other. In this lesson, we have compared the satellite systems in current operation and looked at Kepler's laws, WGS 84, the CA and P codes, and the 3 GPS segments. In the next lesson, we will look in more detail at the principle of operation of GNSS, the importance of time, and how many satellite signals are needed for an accurate position fix. We will also look at system accuracy, errors, and differential GPS, which monitors SV data integrity.